All right, folks, so here we are. It's section 2.43, where we're going to talk about something called non-informative priors. So I think it does a good job of describing what they are. We'll go through the section, and then I'll have a couple of comments that I want to share about the section. Okay, so let's get into it and see what non-informative priors are. So he says, in some applications of probabilistic inference, we may have prior knowledge that can be conveniently expressed through the prior distribution. That's why it's called the prior distribution. For example, if the prior assigns zero probability to some value of variable, then the posterior distribution will necessarily also assign zero probability to that value, irrespective of any subsequent observation of the data. So that's kind of an example of a very informative prior to some extent, right? Because it's telling you that certain values can't happen. So let's just see what he means by that. And that's simply this. So suppose we're interested in some parameter theta. So our posterior on that parameter given the data is going to equal to the likelihood of that data, of those parameters, sorry, times the prior over, this was just Bayes' rule, right? So you can just write this as, something, this P of D is a normalizing factor basically, times P of theta. And now his point is that if we have values of theta where P of theta, so this is of course the prior, if P of theta is 0 somewhere, then no matter what the data says, so no matter what this bit says, if P of theta for a given value is 0, the posterior is going to be 0. So that's that's an example of a very, an instance of a prior being particularly informative around some values, saying that certain values just can't happen. More generally, you can kind of look at this relationship if we think of this P of D, if this is kind of a normalizing factor. You can imagine a P of D given theta. Remember, this is not a probability distribution over theta, but it's just going to have, some form. And then that's going to be multiplied by your P of theta, right? So let's say P of theta had some shape. Then, then the posterior is going to be it's going to be, when you normalize, it's going to look like the normalized product of those two things. So it's going to look like in this particular case, maybe, right? So this prior here is being quite informative, and it's telling us that, and let me actually it's important in this example that everything, all these terms line up, right? So it's telling us that the parameter value is, most likely, unless we have tons of data, going to lie where the prior has some mass, and it most likely won't lie over there, right? So that's kind of a case of an informative prior. It's kind of interacting with our data to constrain the posterior. So what we're looking for now in this section is going to be non-informative priors. So priors that are actually essentially going to leave the data alone. And that's going to mean in somehow essentially having some kind of a flatness property for this prior. So if we had a prior in this case, for example, that looked like that, then the posterior would look just like it did when we, just like the form it had when we just considered the likelihood, when we just considered how the data influenced, how the influence of the data alone, and not, and didn't bring the prior in. So the posterior in this case looks just like the prior, and sometimes we actually want that property. So we're going to talk about very briefly why we might want that, and then how to achieve this, and how and why doing so can be problematic sometimes. Okay, so let me erase this stuff. Okay. So laser pointer I've got. Okay, in many cases, right, so in many cases, however, we may have little idea of what form the distribution should take, right? We may then seek a form of prior distribution called the non-informative prior, which is intended to have as little influence on the posterior distribution as possible. So we don't really know what the prior should be, so but we might still, for whatever reason, need one to do our inference. So we want to pick one that doesn't influence our posterior. So as little influence on the posterior as possible. This is sometimes referred to as letting the data speak for itself. So that's, so this might come up. Okay, so if you have distribution governed by a parameter lambda, we might be tempted to propose a posterior distribution P of lambda equals const. So that's exactly this kind of flat idea that we had before. And this is going to, in the discrete setting, it's going to be okay, but in the continuous setting, it's going to be a bit problematic. So if lambda is a discrete variable with k states, this simply amounts to setting the prior probability of each to 1 over k, right? Because they have to sum up to 1. In the case of continuous parameters, however, there are two potential difficulties with this approach. Okay, so what's the first one? The first one is that if the domain of lambda is unbounded, this prior distribution cannot be correctly normalized because the integral over lambda diverges, right? So if, all that's saying is, what constant value are you going to use when let's say the parameter you're interested in is like the mean of some Gaussian, and it could take any value, any real value. So if you said if the prior probability was some non-zero amount, well, then you have to integrate, you're going to have to integrate that over the entire real line, and that's going to give you, well, it's not going to be a proper probability distribution, right? So if we have, P of lambda is equal to constant, and now you want to integrate, remember one of the properties of probability distribution was that it integrated to 1. Well, for any non-zero, positive constant, if you integrate that over the whole real line, it's going to be infinite. So you're going to have what's going to be called the integral over lambda diverges, such part is called improper. So if we integrate this thing from minus infinity to infinity, it's going to be infinity, right? So yeah. Now, they call improper. It doesn't mean that we can't use them, and indeed we'll see some examples here. I believe where we will end up using them. But it says in practice, improper priors can often be used provided the corresponding posterior distribution is proper. So as long as the influence of the likelihood gives us a distribution, a posterior distribution that does integrate to 1, we're okay. In principle, I believe there are some cases where, like, despite that happening, you can still run into trouble because your prior is not proper, but at least a necessary condition is that your posterior is proper, that your posterior integrates to 1. That can be correctly normalized. For instance, if you put a uniform prior distribution over the mean of a Gaussian, then the posterior distribution for the mean, and that posterior distribution is going to be the product of the likelihood times this prior, and that likelihood itself, if I recall, was a Gaussian. So if you just multiply it by some constant, that constant will drop out when you normalize things, so you'll be okay. Yeah. Okay. So that's one of the problems, right? So this flatness idea is good in principle, but if you have an infinite domain, you're going to run into these issues of not having a proper prior. But it might not be the end of the world. Okay. A second difficulty arises from the transformation behavior of probability density under a nonlinear change of variables. So you might remember this from 1.27, very important. We'll get a couple of chances to play with it here as well. If a function h of lambda is constant, and we change variables to lambda equals, eta squared, then h of eta is, so remember this is the hat, so this is going to be the probability distribution in terms of eta. So h of, notice the hat here, we've just plugged in, so this is actually this function of lambda, but we've plugged in eta squared. So this thing itself will also be constant, but remember that with probabilities, it's not just a matter of plugging in the corresponding value of eta or lambda or whatever it is. There's also this kind of change of variables term, this change of kind of volume term that you have to account for, and that's going to mess things up a bit. So will also be constant. However, if we choose the density p of lambda to be constant, then the density of eta will be given by change of variables formula. Review that if you need to. It's really important here. So this bit was fine, right? That's where that was this. You can just plug in the corresponding value for lambda, which in this case is going to be eta squared. But there's this additional term you have to account for, which is this is going to add a 2 eta there. So now this probability distribution in terms of the changed variable is no longer constant. So this constancy is not preserved over these changes of variables. This issue does not arise when we use maximum likelihood because the likelihood function is a simple function of lambda. So remember, this was not a probability distribution as a function of lambda. So if we change variables, we can just kind of plug in the corresponding value of our parameter in the change setting. But when we're dealing, with the prior, it is a probability distribution. So we have this additional volume term you have to account for, and then when you change variables, that will sometimes mess you up and turn your constant thing into something that's no longer constant. So we're free to write. So if, however, we were to choose a prior distribution that is constant, we must take care to use an appropriate representation for the parameters. And so the question is, what does that mean, right? So the way he's going to define it, the way he's going to talk about it is you're going to say, well, look, we're going to look at the kind of the special, a pair of common properties our likelihood will have. In this case, it's going to be like, remember a couple of sections back we discussed estimating the mean of a Gaussian or the variance of a Gaussian. So we can kind of generalize from those examples a couple of properties of those likelihoods and then try to make our priors so that they maintain those properties. So they'll be kind of informative in that sense, that the resulting likelihood will maintain the property that it had when it's multiplied by these priors we're going to come up with. So let's just see an example of that, and you'll see what I mean. So here we consider two simple examples of non-informative priors. Okay, first of all, if a density takes the form, P of x given mu is equal to f of x minus mu, and the thing you should be thinking about is the mean of a Gaussian, right? So, imagine like this is going to be, the mean of a Gaussian is, I don't know. Let's say we know the variance. Well, this is going to be x. I'm dropping the normalizing terms, and there's going to be x minus mu squared, right? So this is a function of x minus mu. So this is kind of a classic example. This is I think the motivating example here. So we're just going to generalize that because we don't have to deal just with Gaussians. There are many situations where this comes up. If a density takes the form this, then the parameter mu is known as a location parameter. So this is kind of giving you essentially maybe the mean of the distribution in the case of the Gaussian. This family of densities exhibits translation invariance because if we shift x by a constant to give x hat equals x plus c, then we can kind of define a new mean and then we get the same property again. So kind of why is this, why are we talking about shifting x? And I think the reason why we're doing it is because you can imagine that's kind of like getting a new data point or a different data point, right? So how does this likelihood behave? Well, it's like, I guess maybe if you observed a single value, a single data point, maybe you would have a likelihood that kind of looks like this, and this would be maybe sent in the likelihood of, it wouldn't necessarily be a, so this would be P of x given mu. And now suppose you observed another data point, or suppose you can consider another case where you'd observed a different data point that was somewhere else, let's say at over x hat, then the distribution would shift along with it. So I think the idea here is that we're kind of considering what would happen to this likelihood when a particular type of transformation happens to our data. So if our data, if instead of getting one data point, a particular data point, we've got kind of a shifted version of it, which is like, instead of 4, you got -6. What would happen to the likelihood? Well, that whole curve would just shift over. So the shape wouldn't change, it would just shift over. So this is kind of, I think, what he means by translation invariance. If you translate the data by some amount, well, then the likelihood just shifts with it. Okay, so this family of densities exhibits translation invariance, right? Because if we shift x by a constant to give x hat equals x plus c, then, okay, so this is a good opportunity to use our change of our variables formula to make sure that this is the case. Okay, so let's just use this information to figure out what, to essentially derive this expression. And it's really quite simple. Okay, right? So essentially what we're doing is we're changing variables to this x hat thing, right? And so, well, how did that work? And you guys can see all of this, I believe. Okay, good. So we've got, so p of x hat. First, we're going to work with this. So I'm going to change variables to x hat. So we'll stick with mu first, so not mu hat. So this is going to equal to p. Oops. Let me change the size of my my eraser here. Okay. All right. Cool. Okay, so this is going to be p of x, whatever x corresponds to x hat, at mu, given mu, times d of x hat. Now we're lucky in this case because our transformation is really simple. So this thing is just 1, right? And so now what is x? So now what is x given x hat? Well, this is just simply, you just subtract and you get is equal to minus c, right? So then we just plug that in. So we get this is equal to p. So this goes to p of, and this is the original p, this is p in terms of x, minus c given mu. And now we use the fact that, you know, the probability has this particular form. So we say, well, this is the same as p of x hat minus c minus mu, right? But, well, we can just define this, or we can just write this as, you guys can still see, we're going to equal to f of x minus mu, where mu is defined as mu plus c. And so this has the exact same form. So we've just derived this, right? So we've gotten the same form. So basically all we do is we just, if our data point was, you know, was shifted to the right, well, we just define a new mean, but the distribution will look exactly the same. So that's kind of a property that our likelihood has, and we want our prior now to not disturb that property. Okay, so let's continue. So thus the density takes the same form in the new variable as the original one, and so the density is independent of the choice of origin. We would like to choose a prior distribution that reflects this translation invariance property, okay? So we choose a prior that assigns equal probability mass to the interval a's in a to b as to the shifted interval a minus c, b minus c, right? So if the probabilities were different, then that would be reflected in the posterior, and that would be due strictly to the prior. So we don't want that. We want the prior to essentially have this, essentially not care, at least be invariant to this shifting, just like the likelihood is. What we want is that the probability mass between a and b is the same as the probability mass between a minus c and b minus c, and this particular term, notice the limits b minus c, a minus c, is the same as integrating not p of mu, but just subtracting c from it and integrating that from a to b. And the reason why we're doing that is now because we want to compare this to that, and we see that it holds, and we wanted it to hold for all choices of a and b. So I expect there's a theorem in analysis that says that if this is the case, it's kind of quite natural. Sometimes there are weird counterexamples, but anyway, because this must hold for all choices of a and b, we have that. Because, you know, this has to hold for any interval, you can't kind of, yeah, we have that the actual terms being integrated have to be the same, which implies that p of mu is constant. Okay, so in the case where we have this translation invariance property, then we arrive at this conclusion that our prior has to be constant. But you know, we're not limiting our domain to anything, so which means we're going to have kind of we're going to be in a situation where we're in that improper prior situation. So an example of a location parameter would be the mean of a Gaussian distribution, as I've said. As we have seen, the conjugate prior distribution for mu in this case is a Gaussian, and we obtain a non-informative prior by taking the limit sigma squared, sigma naught squared to infinity. So that's just saying, that's just our Gaussian, which is going like this, becoming flatter and flatter. Indeed, from 2 point, yeah, and if you go back up, you'll see, I guess, like you can scroll up. You go back to 2.141 and 2.142, you'll see that in this setting, then all that shows up in the posterior is just terms that are related to data. So there won't be any terms that are related to the prior. All that'll show up, so that you won't end up with mu naught or sigma naught. All that will show up in the posterior is the terms that come from the data, which is what you want. Okay, so that's one example of how we've done. So we've come up with an improper prior because we wanted a particular property, this translation invariance property. Okay, so now let's go on to this second example, which is again inspired by the Gaussian, but now in terms of its variance parameter, or its precision, as we'll work with. Okay, as a second example, consider density of the form this, where sigma is greater than, note that this will be a normalized density provided f of x is correctly normalized. So I think all he's saying is that this thing will integrate over x to 1 as long as this thing integrates to sigma, because then they will multiply and become 1. Okay, the parameter sigma is known as a scale parameter, and you can kind of guess that because you can see that it's scaling x by sigma. And the density scale exhibits scale invariance. So remember we had translation invariance, now we have scale invariance. Because if we scale x by a constant to get x hat is equal to cx, then we get again the same form of this distribution, where we have defined now sigma hat is equal to c sigma. So let's again try this easy example of the change of variables, right? Okay. Slightly more complicated than the previous one, but not too bad. Okay, so we're going to work with, so remember that p of x, we'll work with sigma first, is going to equal to p of x hat given sigma times dx hat. And now, well, so this is going to equal to p of, so now this is the p of x, not x hat, over c given sigma times dx, so that should be 1 over c, right? So that's going to be, and that's the volume element, that determinant element thing. Okay, so now we plug in this term, this identity, and we get that, well, this is going to equal to 1 over sigma times f of x hat over sigma x hat, so we've got the c first, and then it's being divided by sigma times 1 over c, right? So now if we define sigma hat in that particular way, well, we can just, it's very easy to see that this is just the same as f of x hat over sigma hat 1 over sigma hat. So we've got kind of the same form. Well, we do have the same form if we just scale our scale parameter the same way as we scaled our data. So again, here's the situation. You want to see, well, what's happening? What happens to my likelihood if I, for example, get a parameter that's a data point that's 10 times as large or 10 times as small? And the idea is that in that situation where you got a data point that was, let's say, 10 times as large, then the likelihood would shift. It would have the same form, but you know the parameter scale would also be kind of 10 times larger. On the other side, you know, if you got a data point x that was 10 times as small, then again you get the same shape as long as you remember to scale your parameter, to make it 10 times smaller. So that's kind of where the scale invariance comes from. Once you normalize for the scale of the data, things look the same up to some normalizing constant. Okay, so now it says if we consider an interval a and then scaled interval a over c to b over c, a to b versus a over c, b over c, then the prior should assign equal probability mass to these two intervals. Thus we have, so here's the probability mass we're assigning from a to b, and we want it to equal the probability mass we're assigning from a over c to b over c. But that's the same as the probability, as this integral is the same as if we just compute the probability, that probability function, from 1 over, actually evaluate it at 1 over, at sigma over c, so that we can get the same limits of integration as we're getting. Then we also have to scale our sigma parameter there. So we're essentially kind of changing variables to, we're treating this as just a function, but we're changing, when we're integrating it, but we're changing variables to, z is equal to theta over c, so that we get the limits of integration that we want. So this is just the same old p in both cases. And because this must hold for choices for all choices of a and b, we have this must be true. So we're essentially saying that this integrand is equal to that. And hence, this is the case. Okay, so it's not clear to me that this is the only solution. It might be quite obvious, but it's not clear to me. So all I will do here is just verify with you that this satisfies this property that we need. So let's just do that together. So if we have P of sigma is proportional to 1 over sigma, so let's just call it K over sigma. Now then, if we go P of 1 over c sigma, 1 over c is just going to equal to what? It's going to be equal to K over sigma times c, right? So that's this part, times 1 over c, which is K over sigma. So lo and behold, this does hold. Okay, so so I haven't checked whether there are other solutions. Note that again, this is an improper prior, because so if you integrate 1 over sigma, it diverges. It is also sometimes convenient to think of the prior distribution for a scale parameter in terms of the density of the log of the parameter. Okay, so we're gonna get another chance to try out our transformation rules. So let's erase all of this. So notice that what we have here is we've got, okay, P of sigma is proportional to 1 over sigma, so we're going to call it K over sigma. Now the question is, what is P of ln sigma? Right? Well, we know that this is actually going to be equal to P of sigma times d, this, right? Okay, so now we've got, well, this first term is, K over sigma. Now, this is 1 over d ln sigma over d sigma, so times, which is going to equal to K over sigma times 1 over sigma, which is equal to K over sigma times sigma, which is K, which is constant. So in logarithmic parameters, we're assigning a uniform prior if we use the logarithm of the parameter, which is it's a signature of the scale invariance. So if we look at on a log scale, we've assigned equal probabilities. So thus, for this prior, there's the same probability mass in the range 1 to 10 as in the range from 10 to 100 and 100 to 1,000. So that's kind of again, the scale invariance. An example of a scale parameter would be the standard deviation sigma of a Gaussian distribution after we have taken account of the location parameter, because if you look at this, we've defined x tilde as x minus mu, and now we have something, we've got 1 over sigma, and we have some function of x tilde over sigma. So this is exactly what we wanted up here. Now, as discussed earlier, it is often more convenient to work with the precision rather than sigma itself. Okay, so using the transformation rule for densities, we see that a distribution P of sigma of proportion 1 over sigma corresponds to a distribution over lambda of the form, again, of the same actual form. I'll leave that as an exercise for you to do. We have seen that the conjugate prior for lambda was the gamma distribution with the parameters a naught, and b naught. The non-informative prior is obtained for the special case a naught and b naught is equal to 0. And that was because, that was because, so the reason why is because we want P of lambda to be proportional to 1 over lambda, and gamma, this was just a form of it, right? This was a naught minus 1, sorry, it's lambda times x minus b naught lambda, or something like that, right? Let me erase this question. We'll come to this. Right. And so if b naught, so if we set b naught to 0, well then this is going to just go to 1, and this is going to go to 0. So this is just going to equal to lambda to the minus 1, which is 1 over lambda. So this is what we want. So the non-informative prior is obtained in the special case a naught equals b naught equals 0. Again, if we examine the results 2.150 and 2.151 for the posterior, we see that for a naught equals b naught equals 0, the posterior depends only on terms arising from the data and not from the prior. So let's just, in this particular case, let's just look at it just so you know what he means. So we're gonna, a bit of scrolling, sorry guys. Let's just see what he means. I think it's just up here. Yeah, okay, so all he's saying here is, remember this was like we're looking at the posterior on lambda given some data, and you see the parameters are updated with the prior term, a naught plus n over 2, and the other parameter, b naught plus all this other stuff. And if you set a naught and b naught to 0, well then all you get is terms that are coming from your data. So this is just kind of, this is just indicating that our choice of prior was in fact non-informative. Okay, so yeah, that's kind of the non-informative prior. So now we kind of get to some comments about this. So one comment is that I had, so I don't know the answers to these, but if what we care about, if we have terms like this, these kinds of updates, and we have those conjugate priors, then I guess it's just, we don't have to go through these scale invariants arguments necessarily, right? You can just say, well, this is the form that my update takes when I have my conjugate prior a naught and b naught. Well then, if I don't want the prior term to show up, I will need necessarily to set these to 0. So in some sense, there's kind of an easier way. Although I like his approach of coming at it from, maybe sometimes it's not so obvious. So it's kind of nice to be able to see how to do it from some properties that you want your distribution to have, and then kind of derive the functional form of your non-informative prior. Another question is, I mean, if you want the non-informative prior, why not just normalize your likelihood, right? Because your posterior distribution, you essentially want the posterior to look just like the likelihood, but the likelihood is not a normalized distribution most of the time. So why not just normalize it and don't have to go through this whole deal of setting up a prior? And I think it's just that in some settings you might need to start with the prior for whatever reason. So it's not just about that ultimate inference step. Maybe you need to actually start with a prior. So that could be one reason. There might be others. So if you know any others, please indicate in the comments. So that's another reason why it might be useful. It's also just kind of nice to see what form those priors take. But as far as inference is concerned, it might not always be necessary to go through these steps of like defining what the non-informative prior is. Why not just work with the likelihood directly and normalize that? Maybe one reason is that normalization is difficult. Yeah, so it might become clear later on in the book. One other question I had was, so if let's just scroll back down. Yeah. So the question is, why did he introduce all this stuff in this particular section on the exponential family? And I think he doesn't really talk about it here, but I think one reason is that sometimes you're like, well, when you talk about non-informative priors, you actually have some information, some prior information. Like, for example, you know that the mean of the parameter is something, and then you want to use a distribution that is as kind of agnostic as possible. And in those cases, I think we talked about it before, the distribution that you might want to use is kind of the maximum entropy distribution. The distribution that has kind of the maximum uncertainty over the parameters given what you know. And those maximum entropy distributions, I think in every case, are in the exponential family. So that might be kind of some connection to the non-informative prior. So it's, in that case, it would be non-informative in the sense that given the knowledge you have about the knowledge you have about the prior, it gives you a distribution that has the maximum uncertainty. So it's the least informative in that sense. Whereas I think the sense he's talking about it here is that it doesn't touch the likelihood. So there might be kind of two senses of non-informative. But anyway, I think that was kind of a fun run through the non-informative, what non-informative priors are. You might come across them. You'll definitely come across terms like improper priors. All that means is it doesn't integrate to one, but as we saw, it's not necessarily a problem. And then we saw how to come up with priors that respect, let's say, location invariance properties or scale invariance properties of your likelihood. And the idea is that if you might have other properties you want to respect. So these aren't like the only one. So maybe you got an idea of how to do that. Do that here. So I think that is about it. And I think with that we are at the end of the section on section 2.4. So next time we will start by talking about the last section in this chapter on non-parametric methods. So I hope to see you then. Bye.